All right, so in this video, I am going to be talking to you guys about glacier, stress, and strain. So we've already talked a little bit about how glaciers flow and the balance, glacial mass balance, the interactions between accumulation and ablation, and the equilibrium line altitude. And hopefully that video that I shared a link for earlier on this page was kind of helpful for that. But now that we know that glaciers flow, let's talk a little bit about kind of some of the mechanics of how they flow. So I am going to draw our beautiful sort of hypothetical little glacier here. This is our very vertical hill slope. And then we have sort of our block diagram of a glacier here. Blue, of course, because we are thinking about ice. So this is our block diagram. And of course, we know that this is our block of ice. So this ice will have a density of rho I. So rho I is our density of ice. And then we also know that this ice has some height, which we will call h. So h is height of our ice body. And then we also know, of course, we are on Earth. So there is going to be the force of gravity, which will be going downwards. And so then if we sort of think about our block diagram here and sort of think about the forces at play. So we're going to be talking about stress here. So we have stress, which you should hopefully already know about. Sort of the definition of stress and what we're going to be talking about with glacial stress is sort of the measure of how a material is pushed or pulled externally due to external forces. So a measure of how material is pushed or pulled due to external forces. So in thinking about stresses, you've probably heard all this. This is not sort of new to you, but so we have sort of our two types of stress. So if it's a right angle to our surface, we have our normal stress, right angle to surface. And then if it's parallel, that's what we call shear stress. So parallel to a surface. P-A, so hard to spell when you're trying to do this quickly. So P. Probably still spelled that wrong. And this should all be, of course, crazy review for you guys, but I think it's important to just think about this as we're sort of contextualizing this. So as I'm just going to really quick erase this and kind of then jump into our block diagram that we just drew. So now we are going to think about, once I erase this, we are going to think about normal stress for a glacier. And so this value, which we denote as this nice little sigma, as we just talked about, normal stress is going to be sort of perpendicular to our surface, and then it is stress, so it is how it is responding to external forces. And so we just drew up here on our diagram a lot of these sort of external forces that are going on. So the really simple expression for normal stress for our glacier is sort of, again, we have our sigma here. It's just equal to a combination of these factors. So we have our rho I, which is our density of our ice, times the gravitational force, which is G, times our height. And so this is sort of the expression for the normal stress of a glacier. And that's, pretty basic and just sort of the first stab at this, but kind of the interesting thing that we can think about in this normal stress is sort of the importance of this term H, because of course your ice density is not going to change. Ice has a set density. Your gravity is not going to change. We're on Earth, but your height can change. So if we have a very sort of high, very thick block of ice, sort of something that looks, like this big diagram here, then we're going to have a sigma value of normal stress that is also very high. And this should make sense. If we have a larger block of ice, then we're going to be having normal stress. And of course, alternatively, if we have a lower height, a thinner piece of ice or a thinner glacier, then we're going to have a lower normal stress. So kind of continuing this and extending this, we also know, up here at the surface of our ice, right here, your height is 0. And so, as we would expect, if we have our height equal to 0 at the ice surface, then we're going to have no stress, no normal stress. So our normal stress is also 0. And then of course, as we move closer to the ice bed, where we're at our H max, the highest possible, depth of our ice, that's going to be the largest amount of normal stress. So this makes sense if we think a little bit about, the interactions and sort of the flowing at the bed, but this is sort of the beginning of why we again think about glacial erosion, because we have our highest normal stress at the bed. And so this is where we're able to then begin eroding and sort of digging into the bed. So we just talked a little bit about our normal stress and sort of the importance of just setting up our little block diagram here for normal stress. But now we're going to sort of take this one step further. So we talked about normal stress, but now let's talk about shear stress. So as I said before, shear stress is the stress that's parallel to the bed. So shear parallel, this is my little symbol for parallel, stress. And specifically, as I just mentioned, kind of, in thinking about, how the ice is flowing, we're going to be thinking about this type of stress at the bed. So this is actually going to be looking at what we call basal at the bed shear stress. All right. Oh my goodness, my handwriting. And so the symbol that we use for our basal shear stress is going to be this tau basal, which again should not be new to you. I'm sure you've heard lots about this in some of our fluvial material and other stuff that we've worked on already. And so kind of the only real difference with our basal shear stress is that it's largely dependent on this new sort of factor that we're going to be adding in, which is our the angle of our slope here. And so unfortunately, I do not have as many colors as I would like. Otherwise, I'd use super fun color here, but unfortunately, we do not have that. So instead, I'm just going to draw this right in here. And this is our angle right here. And so this is the angle of the slope. And this is what is also going to be contributing to our basal shear stress. And this is an alpha symbol. And so for our basal shear stress, tau beta, it's going to be pretty much the same as our normal shear stress, but it's going to be taking into account this angle because now we're thinking of what's going on parallel to the bed. So it's going to be our rho I times gravity. So all this is just what we had before, times h. And then now we're going to include sine alpha so that we can include sort of the slope here, because if we set this up as like a right angle, if we have our sine of our alpha, sine is opposite over hypotenuse, so that allows us to include the slope itself. And so this value here, or this sort of equation here, is the big one and sort of the big thing that we're thinking about. Oops, I just went through my little b there. Is the big thing that we're thinking about when it comes to glacial erosion, this basal shear stress. So the amount of shear stress going on along the bed. And this is what is going to be able to determine how effectively our glacier is able to then interact with the bed and, of course, erode it. So now I'm just gonna kind of really quick. So glaciers flow because of basal shear stress. So glaciers are able to flow because of this process that's going on. And so, as we have our ice sort of moving this way, we are thinking about basal shear stress. And it varies with the bed. So our basal shear stress really depends a lot on external factors. And so it varies with the bed. And I mean, this should be pretty intuitive to you, but this is important in thinking about glacial landscapes. So if we have a rougher bed, that's going to be very different than if we have a soft bed. And a rough bed could be something like granite or something very hard and able to resist glacial erosion, whereas a softer bed could be some sort of sandstone or some sort of sedimentary rock, which is generally a bit softer. And so this is really important to then begin thinking about glacial flow.